From its perch about 1 million miles from Earth, James Webb has captured extraordinary shots of our solar backyard, while also peering deep more than 13 billion years into the past, at an era when some of the first stars and galaxies were taking shape. But as James Webb delved deep into the first chapter of the cosmic history book, it found unexpected shreds of evidence that shake our cosmology. Look at unprecedented images of the early universe taken by James Webb. Nobody can still hold on to old theories and claim that they are still true. Webb's discoveries present a serious challenge to our best model of how the cosmos evolved. But is the standard model of physics now broken? Join us as we dig deep into how James Webb's view of the ancient universe just shatters our basic understanding of the cosmos. The first billion years of the universe's life were a crucial period in its evolution. In the first moments after the Big Bang, matter and light were bound to each other in a hot, dense soup of fundamental particles. However, a fraction of a second after the Big Bang, the universe expanded extremely rapidly. This expansion eventually allowed the universe to cool enough for light and matter to separate out of their soup and, some 380,000 years later, form hydrogen atoms. The hydrogen atoms appeared as an intergalactic fog, and with no light from stars and galaxies, the universe was dark. This period is known as the Cosmic Dark Ages. The arrival of the first generations of stars and galaxies several 100 million years after the Big Bang bathed the universe in extremely hot UV light, which burned or ionized the hydrogen fog. This process yielded the transparent, complex, and beautiful universe we see today. Astronomers call the first billion years of the universe, when this hydrogen fog was burning away, the epoch of reionization. To fully understand this time period, we study when the first stars and galaxies formed, what their main properties were, and whether they were able to produce enough UV light to burn through all the hydrogen. The first step toward understanding the epoch of reionization is finding and confirming the distances to galaxies that astronomers think might be responsible for this process. Since light travels at a finite speed, it takes time to arrive to our telescopes, so astronomers see objects as they were in the past. For example, light from the center of our galaxy, the Milky Way, takes about 27,000 years to reach us on Earth, so we see it as it was 27,000 years in the past. That means that if we want to see back to the very first instance after the Big Bang, we have to look for objects at extreme distances. Because galaxies residing in this time period are so far away, they appear extremely faint and small to our telescopes and emit most of their light in the infrared. This means astronomers need powerful infrared telescopes, like Webb, to find them. Prior to Webb, virtually all of the distant galaxies found by astronomers were exceptionally bright and large, simply because our telescopes weren't sensitive enough to see the fainter, smaller galaxies. However, it's the latter population that are far more numerous, representative, and likely to be the main drivers to the reionization process, not the bright ones. So, these faint galaxies are the ones astronomers need to study in greater detail. It's like trying to understand the evolution of humans by studying entire populations rather than a few very tall people. By allowing us to see faint galaxies, Webb is opening a new window into studying the early universe. Early galaxies were not like those we know today. The first galaxies were more pristine, composed primarily of hydrogen and helium gas. Over time, their stars would fuse atoms to form heavier elements. And when these stars died in supernova explosions, the heavy elements dispersed throughout the galaxies, enriching them with star stuff, including the elements needed to create life. The first galaxies had yet to settle into majestic spiral patterns or puffy elliptical balls like the galaxies we see around us now. They were far more disordered and much smaller, making them even harder to find. The earliest galaxies we have seen were about 1% the size of our Milky Way, but they were growing rapidly, forming new stars at prodigious rates. Fuel was plentiful back then. Early galaxies were bathed in cool streams of flowing hydrogen gas, lured inward by gravity. The galaxies collided with one another and merged frequently, accelerating their growth and triggering new bursts of star formation. As the universe expanded over time, galaxy growth slowed, significant mergers became less frequent, and the gas supply thinned out. This picture is our basic understanding of cosmic history. We are still working to fill in the details, and many questions remain, especially surrounding the earliest times. When did the first galaxies form? How small were they? What did they look like? Were they building blocks of galaxies to come with single large regions of star formation? Or were they more fragmented and clumpy? Were they all bursting with intense star formation? Or were some more relaxed, like most galaxies today? Did any early galaxies have time to settle into disks like the Milky Way did? Or were they merging too frequently to do so? Will we ever find any filled with pristine hydrogen and helium gas? Or did the first supernovae enrich them too quickly with heavier elements? How rapidly did early galaxies build up in mass and numbers? And were they in fact responsible for reionizing the universe? With the results from James Webb, we are taking another step toward answering these questions. Thanks to its infrared eyes, James Webb is adding a bounty of distant galaxies beyond Hubble's reach and revealing the early universe in far greater detail than previously possible. Webb's images of the early universe have acted like an ocean swell, delivering new waves of evidence. A new research using the James Webb data found that dwarf galaxies in the early universe often look flat, either prolate, elongated along one axis, or very narrow oblate ovals shaped like a surfboard, whereas others have a more frisbee-like oblate appearance. These galactic frisbees seem to grow more abundant as the universe ages, as do the compact, spheroidal-shaped galaxies. As Viraj Pandya, a Columbia University astronomer and lead author of a new paper describing the research, said in a press statement, roughly 50 to 80% of the galaxies we studied appear to be flattened in 2 dimensions. They seem to be very common in the early universe, which is surprising since they are uncommon nearby. The discovery was made using data from CEERS, or Cosmic Evolution Early Release Science, a James Webb program to push back the veil and probe the lives of the oldest, faintest galaxies in the universe. It's an era spanning from 600 million years after the Big Bang to 6 billion years later, during which the galaxies that we see in the universe around us today formed, evolved, and matured, from spirals like the Milky Way and the Andromeda Galaxy to giant ellipticals such as Messier 87. CEERS builds on previous work by the Hubble Space Telescope, which studied the early universe in its deep field images and its Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey program. Hubble found that massive galaxies in the early universe tended to take on the form of oblate spheroids, not dissimilar to the elliptical galaxies of today. Less massive and hence fainter galaxies were more difficult for Hubble to detect, but from what it could see, many of them took on an elongated appearance consisting of chains of brighter blobs, whereas other irregularly shaped dwarfs were nicknamed tadpoles, nuggets, or clumps. The question was, given Hubble's limitations, was it seeing a true reflection of the shapes of smaller early galaxies? The short answer is yes. James Webb's greater vision has now found that Hubble's earlier discoveries hold true. Karthik Iyer, also of Columbia University, described how the greater vision and sensitivity of James Webb, compared to Hubble, is changing the study of galaxies in the early universe. Identifying additional categories for early galaxies is exciting. There's a lot more to analyze now. We can now study how galaxies' shapes relate to how they look, and better project how they formed in much more detail. A picture now emerges of how galaxies may have evolved and grown over time. Matter is distributed throughout the universe primarily in a cosmic web of filaments that span the cosmos. These filaments are predominantly formed from dark matter, with a fraction of normal matter mixed in that forms the galaxies that we observe. The abundance of surfboard-shaped prolate galaxies could be explained by them forming inside halos of dark matter that are elongated in alignment with their cosmic Webb filament. Since other dwarf galaxies would also be forming within that filament, mergers would take place along it, leading to the growth of elongated galaxies that look like chains. Across billions of years, the cosmic Webb filaments disperse and grow more diffuse. The merger rate slows down, and the fraction of prolate galaxies decreases as they start to spin and adopt a disk-like, oblate structure. Such oblate galaxies are seen to increase from 20 to 60% over time and for a given mass of galaxy. Similarly, spheroid galaxies also grow more abundant over time, as compact star-forming galaxies in the universe settle down to become the progenitors of the giant elliptical galaxies we see today, or the spheroidal bulges of massive spiral galaxies. Understanding the evolution of galaxies over cosmic history is a key objective of James Webb. The new findings from SEERS indicate that hierarchical mergers, smaller galaxies merging with larger ones, along the aforementioned cosmic filaments, are key to understanding these varied galaxy shapes. But in addition to its stunning pictures, the Webb telescope has also pinpointed puzzling views that were impossible with previous telescopes. For instance, the telescope has spotted several galaxies in the early universe that appear to be utterly gargantuan, with masses ranging from 10 billion to 100 billion times that of our Sun. Put simply, these galaxies shouldn't exist according to rules laid out in the Standard Model. In other words, Webb's discoveries are stress testing the Standard Model of cosmology, also known as the Lambda Cold Dark Matter Model, exposing an important unresolved issue with the properties of galaxies derived from the observations. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said in an email to Motherboard, "The results have been a real surprise for me, and it's been a very exciting period. I have never seen anything like the frenzy of activity and results that accompanied the release of the first data. Indeed, images captured by James Webb are jaw-dropping on a pure aesthetic level, but Boylan Colchin and other scientists have also found many riddles in the telescope's observations, including those massive galaxies that appear some 500 million years after the Big Bang. These objects really do appear to be early behemoths. They are so massive that we do not expect to have enough collections of atomic matter in the universe at that time to give rise to that much stellar content. So how did these galaxies get so big so fast? Webb's observations suggest that the answer may be linked to the rapid growth of supermassive black holes during the same time period. Virtually all modern galaxies contain a supermassive black hole at their centers, including the Milky Way, suggesting that this is a core feature of large galactic structures. If black holes in the early universe were able to grow to huge masses in a short time frame, it might explain why so many massive galaxies are showing up in the telescope's images. However, this explanation essentially trades out one mystery for another. As Boylan Colchin explained, if it does turn out that massive black holes are making these galaxies appear more massive than they truly are, then we will have other puzzles to understand. How did so many black holes grow so massive so quickly in the early universe? On the other hand, it's also conceivable that some unknown mechanism in the early universe supercharged the process of star formation, which could explain why these early galaxies appear so massive and bright. Another mind-boggling possibility is that these galaxies are packed with a group of stars called Population 3, which are the first stars that ever shone in the universe. Spotting these stellar ancestors has been a major goal in astronomy for decades, but it's extremely difficult to see objects that are this far away in time and space. Population 3 stars are expected to be brighter and more massive than their descendants, which hints that they might be hidden away in the strange galaxies seen by James Webb. However, if none of these explanations ultimately fit, It may be time to consider whether these ancient galaxies have exposed a fundamental gap in our understanding of the universe. Perhaps the observations made by James Webb are telling us that our standard and very successful lambda cold dark matter model is incomplete, that we're missing a component. There are clues that this is the case. Calculations of the expansion rate of the universe based on measurements at early cosmic epochs don't agree with direct measurements in the local universe, for example. And some proposed solutions to this disagreement, which is called the Hubble tension, involve adding additional dark energy at very early times, only 50,000 years after the Big Bang. An interesting byproduct of these early dark energy models is that they predict faster evolution of structure and more structure at high redshift, which is exactly what would help explain the existence of these massive early galaxies. It is intriguing that a single solution might explain both of these observational discrepancies. In short, one thing is clear. Scientists have their work cut out for them in terms of unraveling the true meaning of these bizarre images. To that end, future observations can help to confirm that these galaxies really are that massive, and astronomers also plan to look at much bigger patches of sky to make sure they aren't seeing a fluke that is limited to one region. However, for now, we will all have to uneasily sit with the unexplained presence of these galactic giants at the edge of space and time. Meanwhile, in another observation made by the Hubble Space Telescope, astronomers have just discovered that the atmosphere of a relatively small planet outside the solar system is rich with water vapor. However, don't plan a vacation to this destination just yet. The planet's surface is hot enough to melt lead, meaning it's a steamy world inhospitable to life as we know it. More specifically, the team behind this finding says the extrasolar planet, or exoplanet, named GJ9872d, exhibits Venus-like temperatures of 752 degrees Fahrenheit or 400 degrees Celsius. But that doesn't make this discovery any less exciting. Though scientists have found water vapor in the atmospheres of many extrasolar planets before, the Hubble telescope's observations of this hot and steamy world, designated GJ9827d, represent the smallest exoplanet around which this vital element for life has been found thus far. As Laura Kreidberg, team member and director of the Max Planck Institute for Astronomy's Atmospheric Physics of Exoplanets department, said, "The discovery of water on GJ9827d is exciting because it's the smallest planet yet where we've detected an atmosphere. It pushes closer than ever to characterizing truly Earth-like worlds." Elsewhere, astronomers has just witnessed 18 ravenous black holes ripping up and devouring stars. This result, made by a team from the Massachusetts Institute of Technology, more than doubles the number of gruesome, star-shredding tidal disruption events seen in the local universe. The findings could help astronomers better estimate the number of tidal disruption events occurring across the universe, bringing the rate closer to theoretical predictions. Tidal disruption events occur when a star gets too close to a black hole, and the latter object's gravitational influence generates tidal forces in the star so great that the stellar body is stretched vertically while squashed horizontally, a process called spaghettification. The material from the star forms a flattened disk around the black hole, with some of it accreting to the black hole's heart, while other stellar matter is channeled to the poles by powerful magnetic fields and blasted out as near-light-speed jets. Previously, astronomers had believed that black holes rip apart and devour stars while blasting out highly energetic jets in galaxies that have recently undergone periods of intense starbirth called starbursts. However, this research implies tidal disruption events can occur across a wider range of galaxies and could help explain the extreme physics seen around such events. As Erin Kara, team member and an assistant professor of physics at MIT, said in a statement, "People were coming up with very exotic solutions to these puzzles, and now we've come to the point where we can resolve all of them. The MIT team began searching for more star-devouring black holes after they discovered the closest tidal disruption event to Earth ever seen. It was witnessed in the form of a flare from the galaxy NGC 7392, located around 137 million light-years from Earth. This opened up an entirely new way to spot actively feeding black holes, they said. It involves using infrared light and an algorithm that hunts for patterns in infrared data that indicate brief or transient bursts of radiation. The technique completed was based on historical data collected by NASA's Wide Field Infrared Survey Explorer, or NEOWISE for short. Since its launch in 2009, NEOWISE has been searching the sky over Earth for brief bursts of infrared light. The team then cross-referenced the transients they found with a catalog of galaxies within a distance of 600 million light-years of Earth, revealing that the infrared bursts could be traced back to about 1,000 galaxies. Zooming in on these galaxies, the researchers attempted to discover if the signals they had detected came from tidal disruption events, or if they could have been triggered by other violent events, such as the supernova explosion of a massive dying star. It'd also have been possible for them to come from supermassive black holes at the hearts of galaxies as they feed on in falling dust and gas. This ultimately led to the discovery of 18 legitimate tidal disruption event signals that were the result of the gravitational influence of black holes generating tidal forces in stars that eventually led to some gory stellar deaths. Surprisingly, the team found that tidal disruption events seem to occur across a range of galaxies across the entire sky, including ones that are filled with thick clouds of dust. According to research lead author and MIT's Kavli Institute for Astrophysics and Space Research graduate student Megan Masterson, if you looked up in the sky and saw a bunch of galaxies, the tidal disruption events would occur representatively in all of them. In the grand scheme of things, this research helps settle some major questions surrounding tidal disruption events. Previously, astronomers had mainly seen these star-shredding occurrences happening in post-starburst galaxies with stellar factories that had recently shut down. Such galaxies are fairly rare, and scientists were confused as to why tidal disruption events seemed restricted to them. This research alleviates that confusion by finding gory tidal disruption events in a spread of galaxy types. The reason tidal disruption events were seemingly absent from other galaxies is that, whereas post-starburst galaxies are devoid of thick gas and dust because they exhausted the materials, while creating a wealth of new stars, other galaxies still have the material in abundance. Gas and dust are adept at absorbing or blocking optical and X-ray light, but infrared slips through the matter more easily. Thus, X-ray and optical emissions were fine for spotting tidal disruption events in dust-depleted galaxies. But infrared observations were key in finding star-shredding black holes in dusty galaxies. It's not that they're only occurring in one type of galaxy, as people thought based only on optical and X-ray searches. If you want to understand tidal disruption events as a whole and use them to probe supermassive black hole demographics, you need to look in the infrared band. The findings from the MIT researchers could also explain why tidal disruption events don't seem to radiate as much energy as is predicted by theory, with the team suggesting that the energy deficit is the result of dust-absorbing optical and X-ray emissions, as well as extreme ultraviolet radiation from tidal disruption events. Adding the 18 new tidal disruption events they discovered to previously observed events of this nature, the MIT team estimates that galaxies experience a tidal disruption event roughly once every 50,000 years, which is in line with previous theoretical predictions. As Kara concluded, this gives us confidence that we don't need all this exotic physics to explain what we're seeing, and we have a better handle on the mechanics behind how a star gets ripped apart and gobbled up by a black hole. We're understanding these systems better. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.